In today's lesson, we're going to continue with our study of integration by parts and deal with functions that incorporate exponential functions. So say we're asked to integrate x times e to the x. And again, remember our rule, our Lippitt anacronym. A polynomial comes before an exponential, so we're going to let u equal x, and dv is going to equal e to the x dx. So du is dx, and v is e to the x. So therefore, our integration by parts is u times v, so it's going to be x e to the x minus the integral of v, which is e to the x du, which is dx. So this is x e to the x. The integral of an exponential is itself plus a constant, and that would be our final answer. All right, in our second example, again, same idea. We're going to let u equal our polynomial x. dv is e to the negative 2x dx. du, again, is going to be dx. And when I integrate dv to get v, the integral of e to the negative 2x is e to the negative 2x divided by negative 2. So therefore, my formula is uv minus the integral of v du. So u times v is going to be x times negative 1 over 2 e to the negative 2x minus the integral of v du, which was dx. So cleaning this up, negative 1/2 x e to the negative 2x. I can bring the negative 1/2 out front. That becomes a positive 1/2, and now it's the integral of e to the negative 2x dx. And the integral of e to the negative 2x, we did that earlier, is e to the negative 2x divided by negative 2 plus my constant. So my final answer is going to be negative 1/2 x e to the negative 2x minus 1/4 e to the negative 2x plus a constant. And that would be my final answer. All right, next example. Same thing, I'm going to let u equal my polynomial. du is now 2x dx. My dv is e to the x dx. So if I integrate that, I get e to the x. So now setting up my integral, it's going to be u times v, which is going to be x squared times e to the x minus the integral of v du, which is going to be e to the x, which is v, du. I'm going to put the 2x out front. So now I'm back to another integration by parts. So to enable to do this, I have to use integration by parts again. So this time I am going to let u equal 2x. And dv again is e to the x dx, so the integral is again e to the x, and the derivative is going to be 2 dx. So now, when I get back to my question, I have x squared times e to the x minus, now I have to do integration by parts, again, to what's highlighted in green there, so u times v is going to be 2x e to the x minus the integral of v, which is e to the x du, which is going to be 2 dx. So x squared e to the x, I distribute, I get minus 2x e to the x plus the integral, I'm going to bring the 2 out front, of e to the x dx. And finally, my last line, you have x squared e to the x minus 2x e to the x plus 2, the integral of e to the x is e to the x plus a constant, and that would be my final answer. Again, if you want to try this one, you can. This one, you only have to do it 3 times. And again, for this one, I'm going to review the table method. And remember, when we're doing a product, I have my x to the cubed, and I have my e to the x. Provided one of my terms, when I take the derivative, will go down to 0, I can use the table method. And e to the x is just e to the x. And remember, I do this derivative along this table as many times as I've done the derivative there. And then I multiply those together, those together, those together, and those together. And again, my sign is plus, minus, plus, minus. So my answer is going to be x cubed times e to the x minus 3x squared times e to the x plus 6x times e to the x minus 6 e to the x plus a constant. And there would be your final answer, as opposed to having to integrate it 3 particular times. Okay, in our next example, we have the integral of e to the x times cos x dx. And again, using our Lippitt rule, exponentials come before trig, so I am going to let u equal e to the x. dv is going to be my cos x dx. So therefore, my integral of cos is sine, and my derivative is going to be e to the x dx. So now, if I was to set this up, I'm going to start again with my original question, and the reason is because for this particular problem, I want to end up with an integral or something that's going to be the same form as my original question. And just to, before we do the use of integration by parts here, notice my 2 terms here. I have e to the x and cos x. If I tried to do the table method, taking the derivative of e to the x would just keep being e to the x, and the derivative of cos x is negative sine, and negative sine would be negative cos, and neither of these would work their way back down to 0, like in this previous example where x to the third got down to be 0 by taking the derivative continually. So the table method would not work in this case. So that's kind of an indication that when we do the integration by parts, we're going to end up with something in our answer that's going to be the same term as our original question, and then we'll finish it off very similar to what we did in the first video of integration by parts. So again, here's my question, and then we'll go through the integration by parts, which is u times v, so e to the x sine x minus the integral of v, which would be sine x e to the x dx. Again, I'm going to use integration by parts for this part. And again, our Lippitt rule again, u is going to be e to the x. dv is sine x dx. And the integral of sine is negative cos, and the derivative of e to the x is e to the x dx. So again, I get my original question equals e to the x sine x minus, now I'm doing integration by parts to the highlighted part, so it's going to be u times v, so it's going to be negative e to the x cos x minus the integral of v du, which is going to be negative e to the x cos x dx. So now, here's my original question again. E to the x sine x, the double negative when I distribute becomes plus e to the x cos x. This negative can come out to be a positive, and when I distribute that, this is going to be minus the integral of e to the x cos x dx. Now, notice this is the same as my original question. So I'm going to add that over to the other side. So I'm going to get 2 integrals of e to the x cos x dx, and that's going to equal e to the x sine x plus e to the x cos x, and then my constant. And finally, the last thing I need to do is I need to multiply it by, or divide everything by 2. So this is going to be 1/2 e to the x sine x plus e to the x cos x plus a constant, and that would be my integral of e to the x cos x dx. So again, you can try this one here. Not that one, sorry. This one here. Let's look at e to the negative 3x dx. And again, to do this one gets a little bit messy again. But again, this is one of those questions where you're going to have to try to get something in your answer that is similar to your original question. So to begin with, I'm going to let u equal e to the negative 3x, and dv is going to be sine x dx. So the integral of sine is negative cos, and the derivative of this is e to the negative 3x times negative 3 dx. So now, using my u substitution, I'll start with the original question. So e to the negative 3x sine x dx is going to equal u times v, which is going to be negative e to the negative 3x cos x minus the integral of v du. And if you multiply v and du together, okay, well, you have a negative 3 times a negative cos, so that's going to really become a positive 3. And then I'm going to have a cos x times e to the negative 3x dx. So therefore, if I clean this up, I'm going to get e to the negative 3x sine x dx, which is my original question, is going to be equal to negative e to the negative 3x cos x. I'm going to bring this 3 out front because it's a constant. And now I have to use integration by parts again to integrate that part. So now in this part, I'm going to again let u equal e to the negative 3x, and du is going to be negative 3e to the negative 3x dx. dv was cos x dx, so v works out to be sine x. So again, we have our original question, e to the negative 3x sine x dx is equal to negative e to the negative 3x cos x minus 3 times, using integration by parts, it's going to be e to the negative 3x times sine x, so that's u times v, minus the integral of v du, which is going to be negative 3 e to the negative 3x times sine x dx. So, our original question again. I'm going to distribute the negative 3, so I'll make a negative 3 e to the negative 3x sine x. This negative comes out front to be positive, and times by the -3 will become -9. The integral of e to the -3x sine x dx. Now, if you notice, this is the same as this. I have one of them over here and -9 of them over there, so I'm going to add the 9 to the other side. So I'm going to end up getting 10 integrals of e to the -3x sine x dx is going to equal -e to -3x cos x minus 3e to the -x sine x plus my constant. And now I just divide everything by 10. And it's going to be 1 over 10 times the negative of e to the -3x cos x, be a negative there, minus 3e to the -x sine x plus my constant, and there would be your final answer. Again, an ugly question, but one that you can handle if you go through the same procedures you did on the previous one, except now we get a 10 over here instead of a 2. Okay, the last one here, this one gets a little ugly, and I'm only going to show you one like this, just to show you the depth that some of these can get to. Again, by taking the derivative of 2 to the x, you'll never get 0, and sine to the x, you'll never get 0. So you must be thinking, we need to try to generate an integral that's going to look similar to the original question, and then we'll clean it up just like we did this last one. So again, using our Lipit rule, u is equal to 2 to the x. dv is going to be sine x dx. So v is negative cos x. And du, remember the derivative of an exponential base a is itself, times the derivative of the exponent, which is 1, times the natural log of the base. So now we've got our u and our v. So now our original question is 2 to the x sine x dx equals u times v, which is going to be negative 2 to the x cos x minus the integral of v du, which is going to be negative cos x 2 to the x ln2 dx. Okay, so let's clean this up a little bit. And you just have to go slowly with these, and they usually work out quite nicely. This negative can come out front to be a positive. ln2 is just a constant, so I'm going to bring him out. And I'm left with 2 to the, 2 to the x cos x dx. And now I'm going to apply integration by parts to that. So u is going to be 2 to the x. du is cos x dx. So v is sine x. And du is again 2 to the x ln2 dx. So my original question again, 2 to the x sine x dx equals negative 2 to the x cos x plus ln2. And now I have to take the, I have to take the integral of this using integration by parts again. So it's going to be u times v, which is 2 to the x sine x minus the integral of v du. And the integral of v du is going to be 2 to the x ln2 times sine x dx. So we're getting very close here. I have 2 to the x sine x dx, which is my original question, is going to be negative 2 to the x cos x plus, now when I distribute the ln2, I'm going to get ln2 times 2 to the x sine x. And when I bring this ln2 in front of this integral and times it by ln2, it's going to be ln2 squared, the integral of 2 to the x sine x dx. And notice this is the same as this, but I have negative ln2 squareds of these, so I have to add this whole thing to the other side. So when I do that, I am going to get ln2, well, yeah, I'm going to get ln2 squared integral 2 to the x sine x dx plus my original one and that's going to equal negative 2 to the x cos x plus ln2 2 to the x sine x. So now I have a common factor here of integral 2 to the x sine x dx. So if I factor that out, and again, a lot of you could do this in one step prior, I'm going to get 1 plus ln2 squared times the integral of 2 to the x sine x dx equals negative 2 to the x cos x plus ln2 2 to the x sine x. And before, just like I divided by 10, I'm going to divide by this ugly binomial. So it's going to be 1 over 1 plus ln2 squared times negative 2 to the x cos x plus ln2 2 to the x sine x, and that would be your final answer. Oh, and my plus c. So again, you can see these can get a little bit tricky, but if you do them step by step, they're not too bad. And this one here, would I give you an assessment one like this? Probably not, but just wanted to show you again the depth that some of these questions could go to. Okay, so your assignment today is right here, and you can give this one a whirl. And the reason I did that last example was for your question number 5 and your assignment, but you can give it a try, and that concludes the lesson for today.